Okay, so let's start this session. Good evening, everyone. Myself, Arka Roy. I'm working as a Prime Minister's Research Fellow in the Department of Electrical Engineering, IIT Patna. And I'll be your NPTEL PMRF TA for this course on discrete time signal processing. This course is offered by Professor Mrityunjay Chakravarti, who is a professor in the Department of Electronics and Communication Engineering, IIT Kharagpur. So generally, I used to take this class on each Friday, but due to some reason, I have preponed this class on Thursday. So I'm recording this class on Thursday itself, and I will be uploading this video by tomorrow itself. So let's start with the presentation layout. So in this week, in this particular live session, we'll be solving the week 6 quiz. Followed by, we'll have some quick recap of week 7 content. So in week 7, the main theme is basically the design of IIR filters. And uh, in addition to that, we have impulse invariance method, impulse invariance method. And we just have started uh, bilinear transform. Bilinear transform. So we'll mainly focus on impulse invariance method and how we can construct an IIR filter. So there we'll see that we'll have to first design a equivalent analog. So we need to first design an equivalent analog filter, and from that analog filter will be able to construct an IIR filter. So directly we cannot design an IIR filter. So first we need to design an equivalent analog filter, and for after that we need to just remap that analog filter into a digital domain. So we can do it using impulse invariance method. And associated with that, as because we need to construct the filter in the analog domain, so we need S transform, which is also known as the Laplace transform. So we'll see these related topics also, that how Laplace transform is basically used to design the analog equivalent filter of that particular IIR filter. So let us start with the week 6 quiz. So in week 6, the main topic was the introduction to FIR, IIR filters and their structures. So we had seen that there are structures such as lattice structures, then cascaded structures. Followed by that, we had seen some parallel structures also, then direct form 1, direct form 2. And we had seen that how the coefficients of an FIR filters are related. So there are symmetry properties. So we had visited the mm, if the number of the finite number that is basically there in case of finite impulse response filter. So if that number of coefficient is even and if the number of coefficients are odd, then how the symmetricity property is basically exploited to generate the filter coefficients. So with this, let us start solving the week 6 quiz. So this is the first question. So in this particular question, we have been given a system. So in this particular system, the xn is basically the input signal, and followed by that yn is the output signal. Now, given this is the filter response. So this is an IIR filter, and why this is IIR filter? Because we can see that the output is basically related with the current input, past versions of output, and at the same time we can see that it is also related with the past versions of output itself. So as because the past versions of outputs are also incorporated, uh, So therefore, we can say that this particular filter has an IIR response, or we can call it as an infinite impulse response filter. Now, given this particular system, we need to find what is the relation between yn and xn, and obviously there will be several terms which are also related to the past versions of the output as well as the delayed version of the inputs itself. So let us start solving this particular question. So let Vn be the intermediate signal. So instead of going with xn directly, let me just consider Vn as another intermediate signal, and Vn is basically going at the output side. So it's a combination of Vn and xn to get the output Yn. So let us start forming the equations of this particular half. So I'm marking this area. So for this particular region, let us first try to configure the equation, the governing equation. So we can see that xn is coming from here, and some delayed representations are also delayed representations of Vn is coming through this particular path. So there are three paths. So from these three paths, some inputs are coming, and then there is a adder. So this adder is basically accumulating xn and the delayed versions of Vn. And then whatever signal is going out, that is actually the Vn signal itself. So therefore, I can write at for this particular, let me start writing the equation from this particular side. So x, oh, let me just change the color. So I can write that Vz is equals to, it is equal with x of z. I'm writing in the z domain, x of z. Then this is the first delayed output, so which is basically added with xn. So this is what Gn, and it is delayed with z to the power -1. So let me just write in the z domain first, and then I will move to the time domain or the sample domain itself. Along with that, there is a multiplication factor is also associated with this. So this multiplier has a gain of half. So half will also be multiplied with this particular representation. Thereafter, Vn is also going passing through this particular delay, and this is the second delayed block. So at this delay block, so I am getting Vz multiplied with z power -2, as because there are two delays. After that, so this is passing through this third delay block, which has z to the power -2. So therefore, effective delay will be z to the power -4 multiplied with Vz, and there is a multiplying factor of -half. So therefore, -half will also be incorporated over here. So I can write it as Vz is equals to x of z plus half into z inverse Vz plus z to the power -2 Vz minus half z to the power -4, then Vz. So I can form a Vz upon xz, and I can write it as 1 divided by 1 minus half z inverse minus z to the power -2, and it will be half z to the power -4. Okay. So this is one particular transfer function, which is written in Z domain, obviously. And additionally, I can write similar kind of equation for this particular half. So where output is related with Vn. So for this black half, so this is basically coming from the red half. And now let's construct the governing equation for this particular half. So at this particular condition, I can write it as y of z. It is related with v of n. So in z transform, it will be v of z. So this particular line is basically giving you v of z. In addition to that, there are two delay blocks are there. So it will be So it will be z power minus 2 and there will be v of z and there is a multiplying factor of minus half is there. So I will multiply a minus half over here and in addition to that we have a third delay component. So therefore z to the power minus 4 multiplied with vz. So this is the equation for this particular case. So let me construct another transfer function yz upon vz. So yz upon vz, I can write it as 1 plus z to the power minus 4, then minus half into z to the power minus 2. So this is basically the transfer function for the second half, for this particular half. So now we need to find what is the overall transfer function. That means yz upon xz. So I can write yz by vz and then vz by xz. So now I can see that, okay, we have the representations already worked out. So yz upon vz is given over here and similarly vz upon xz is given over here. So let me just plug in this particular relations and then let us see that what is basically there in the transfer function of yz upon xz. So let me just copy these parts in the next page. So it will be vz upon xz over here and we'll have yz upon vz. So this particular half will be over here. So we can now check that vz upon sorry. So now we can see yz upon xz is equals to yz upon vz multiplied with vz upon xz as we have seen previously. So let me just plug in the relations. So 1 plus z to the power minus 4 minus half z to the power minus 2 divided by 1 minus half z to the power minus 1 z to the power minus 2 plus half into z to the power minus 4. Now this is basically what is yz upon xz looks like. Now I can cross multiply these relations. So yz multiplied with 1 minus half z inverse minus z power minus 2 plus half z power minus 4. And likewise, I can cross multiply this part also. So 1 plus z to the power minus 4 minus half z to the power minus 2. Now let's take inverse z transform in both sides. So if I take z transform in both the sides, so I will get for this particular relation, it will get yn followed by minus half, then y of n minus 1. Because it is obvious that we have a delay of 1. So yz multiplied with z to the power minus 1. If I take inverse z transform, so I will get y of n minus 1 as because there is a delay of 1. Likewise, I will get y of n minus 2 as because here I have delay of 2 and then half y n minus 4. OK, so here I will get x of n followed by x of n minus 4 minus half x of n minus 2. OK, so now I just need to rearrange these functions. So let me see first how the results have been given in the options. And if it is required, then I will start arranging the operators. So the answer that we have found is this one. So let me just copy this part over here and let me reduce it. So this is what we are getting. So write the next part, that is half of x of n minus 2. Sorry. So this is what is half x of n minus 2. Okay, so let's start matching the options. So y of n minus half of y of n minus 1, y of n minus 2, half of n minus 4, x of n minus half of x of n minus 2, and followed by there is a plus x of n minus 4. So in this particular question, this option A is the correct answer. So let's move to the next question. In the next question, they have been given that there have been uh, filter is given. So this is also infinite impulse response of you can just consider there is a response is basically given in the terms of the yn and xn, and the impulse response of hn is given by. So the question is that we need to find the impulse response of this particular system. So this is the system. So we need to find x of n. If I just draw the equivalence model, so the equivalent model is given this system hn. So we are providing the input xn and the output is yn. So we need to find what is there inside this particular h of n. So we need to formulate the filter coefficients for this particular system. Okay. So for this particular system, let me start writing the relation between yn and xn. So the relation between yn and xn can be observed as, so there are three particular adders are there. So one output is coming from here. Okay, so there is second output. Then these two are added. So these two will be passed through this particular adder, and then the third component is adding over here. So this 1, 2, 3 will be added and then it will be passed. And then there will be a fourth component which will be passed through this particular adder. And then we'll get first component, second component, third component, and the fourth component. And this 4 component addition will give me the value. So let me start writing the first component itself. So yn is equals to. So I have to first check this particular operation. So this particular operation I need to check. So we can see that xn is actually passing through xn is passed through several delay blocks. So we have to cautiously calculate that how many delays that is the xn is basically seeing. So therefore, at this particular region, when the output is coming at this particular first path, so we can see that xn is passed through all delay blocks. So it will be 1. Then 3, 4, 5, 6, 7, 8, 9. So there are 9 delay blocks. So x of n minus 9. And then there is a multiplication factor of half is there. So half. Okay, so first component we have achieved. Then we need to talk about the second component. So the second component is basically coming from this path, let's say A, and this path B. So A and B is added, then minus half is multiplied, and then we'll get the second component. So obviously we can see there is a multiplication factor of minus half, and the operand that is there is basically summation of A and B. So we need to say that what is A and what is B signal is coming over here. So this will be x of n minus 1 A, as because this has seen only single delay, and thereafter I need to check that how many delay blocks have been covered at this particular position. So 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 delay blocks, so I can write it as x of n minus 8. Okay. Now we need to find the third component. So for the third component, we can see this just as single there are no multiplicative factors have been associated at this particular path. So this is just a result of summation of C and D. So let me start writing what is the output at C and D, and then we'll add these two. So at C position, it is seeing two particular delay blocks. So it will be x of n minus 3, and then it will be x of 1, 2, 3, 4, 5, 6. So x of n minus 6. And the last component, that is the fourth component, is basically the there is an addition of E and F, and then there is a multiplication factor of -1 is associated over here. So that means -1 is multiplied with E plus F. So at E, it is seeing 1, 2, 3, 3 delay blocks with a delay of 1, 2, 3, 4. So x of n minus 4, followed by at F condition, there is another delay is provided over here. So x of n minus 5. Now just rearrange the operator. So x of n minus n minus half x of n minus 1 minus half x of n minus 8 plus x of n minus 3, x of n minus 6 minus x of n minus 4 minus x of n minus 5. So and there have been another path probably. So it is coming over here. OK. So yn, I can arrange all the components in this particular fashion. So it will be minus half x of n minus 1, followed by that there will be x of n minus 3, followed by that there will be minus x of n minus 4. I'm just arranging in terms of the delay. So there is a first delay, then second delay, then third delay, fourth delay, likewise. So there is no a component with the delay 2. So therefore, we can consider there is the coefficient corresponding to the delay 2 is basically 0. So that will take care of at the end while finding the coefficients of the filter. So it will be next component is minus x of n minus 5, and then plus x of n minus 6, and followed by that there is x of n minus 6. Then 7 is not present, so therefore the next component will be x of n minus 8. So this will be minus half x of n minus 8. And then there is a component of x of n minus 9. So half x of n minus 9. OK, so here while calculating the first component, so the first component is basically a multiplication of half with the summation of these particular blocks. So at this particular, we have considered the z to the power minus 9 delay. So we also have to consider the x of n over here that we just have missed. So it will be x of n, and the half is multiplied over here. So there will be a factor of half of x of n, half of x of n. So this is what the final relation looks like. So let me just copy this particular relation, and then we are good to go with finding the final coefficients. So therefore, let me just copy this part over here. So the system looks like this. Now we need to find what is the coefficients of that particular h of n. So h of n, how I can get is that, for example, I can take yz, and over here I will also take the z transform. I will take Z transform over here of this whole thing. So I will get something yz is equals to, let us consider this is p of z and multiplied with x of z. So yz upon xz will be p of z. So this p of z will also be a form of nz by dz. So there will be numerator factor and denominator factor, as because this will give you some representation of transfer function. So transfer function contains the numerator and denominator part. So in numerator part will also be a function of z and denominator part will also be a function of z, and yz upon xz. So from the first lecture itself, we are seeing that yz upon xz is basically the system transfer function, that is h of z. Now, if you just take the in IDF IZ transform, that means inverse Z transform, so you will get what we call it as h of n. So given this particular relation, we can actually formulate how the coefficients of h of n looks like. So half x of n minus 1, then followed by 0 into x of n minus 2, and then it will be x of n minus 3 minus x of n minus 4, x of n minus 5, and half of, and the seventh component is missing, so I can again write it as 0 into x of n minus 7, and then I can write it as half. So sorry, there is minus sign been associated over here. So minus half x of n minus 8, and then plus uh, half of x of n minus 9. Okay. So now we need to find the coefficients. So it will contain the coefficients in this particular manner. So half, 0, 1, minus 1, 1, 0, minus half, and then half. So this is basically the coefficient distribution, how the coefficient looks like in this particular h of n. So let me just copy this answer and let us try to match with the given answers. So this is what we have found, and let's just check with which option it is basically matching. So it is half, then minus half, then 0, 1, minus 1, minus 1, 1, 0, minus half and half. So option C is the correct answer for this particular question. So let's move to the third question. So in the third question, it is given that XAT is an analog square pulse with height 1, and it is located in between these particular intervals 0 to 1. And the equation is given as XAT is equals to UT minus UT minus 1. So that means there are two unit step signals. One is starting from 0, and one there is a delay is given over here, u of t minus 1. So that means there is a delay of 1. And we have negated these two signals so that we can get square pulse. So how the square pulse is coming? So if I just show you, so this is what is ut looks like, so 0. And this is what u of t minus 1 looks like, u of t minus 1. So it is starting from 1. So if we just negate these two signals, so in between 0 to 1, so it will be 1 minus 0. So the amplitude will be constant 1 till the position of 0 to 1. After that, whatever signal is there, this is matching with the value amplitude of ut and ut minus 1. So if I just negate these two, it will give me 0. So this is how I am getting a square pulse over here, and the amplitude is 1. So this is XAT. The governing equation is UT minus UT minus 1. Okay. Now we need to find the range of this particular signal. So whether the range of the time. So for that, XA 4t minus 1. So we can see there are several composite operations have been applied. So in the first lecture, I had told that if in any signal there are composite operations have been applied, so we need to, in order to draw that particular signal, we have to check the signal from the right side and we have to go towards the left, from right to left. So the first operation is delaying the signal by an amount of 1 unit. So I will first delay this signal by an amount of 1. So it will be 1 and 2. So this is delay by 1 unit. So this is the first operation. Now in the second operation, I can see there is a time scaling property has been applied. So in the first lecture itself, I had told that if x a alpha t is given, so you've been given xt, and you need to draw the x of alpha t. So alpha, there could be two cases: when alpha is greater than 1, when alpha is less than 1. So when alpha is less than 1, so this basically gives you compression, and when alpha is uh, less than 1, so then it gives you expansion. So you can check the week 1 lecture. So in week 1, in the live session itself, I had solved several problems related to these particular representations. So in the first question itself, I had considered probably 5 to 6 questions over there. So you can just look those problems and then you can refer to that particular material. So with this, if I now here I have alpha, which is greater than 1. So obviously it will give me a compression effect. So if I see the compression effect, it will be 1 divided by 4. I will be dividing with the same factor alpha. Each and every point I'll be dividing with the same factor. So and this part will be 2 by 4. So therefore my signal will now have a range of 1 by 4 to half. So therefore I can say this is basically xa 4t minus 1. So this is how the signals looks like, and this is lying in the range of 0.5 to 0.25. So therefore, so this is the final answer. 1/4 to half. Okay, let's move to the next question. In the next question, we can see a relation have been given if yt is equals to xat, and this is a convolution operation over here. So xat and it is convolved with xa minus t plus 10. And xat is the analog pulse which have been given in the last question. So this is the last question. In the last question already they have given how xat looks like. Now I need to find what is the range of yat. So let me just change the color. So yat is equals to xat convolved with xa minus t plus 10. So let me just try to draw these particular signals. So this has a range of 0 to 1 and it is convolved with xa minus t plus 10. So here also we can see that composite representation have been composite operations have been applied. So first operation is advancing operation. So I will advance this particular signal with an amount of 10 unit in the left hand side, as because in case of advancing the signal goes to the left part of the plane. So 0 will go to minus 10 and this one will go to minus 11. Now this is what advancing looks like. Advancing operation is the first operation. And the second operation is basically the time reversal operation. So time reversal operation, it will just act as a mirror. So this y-axis will act as a mirror, and whatever is coming over here, that will be replicated in the positive half side. So here I can write it as 10 to 11. So this is what xa minus t plus 10 looks like. So I can directly write it as 10 to 11. So if I have to write the equations in terms of equation, if I have to construct, so it will be ut minus 1. Just now we have seen that how ut and ut minus 1 uh, gives this particular representation square pulse. Likewise, I can write it as u t minus 10 minus u t minus 11. Now I'll be applying the convolution operation in between these two particular signals. So ut convolve with ut minus 10 minus ut convolve with ut minus 11 minus ut minus 1 convolve with ut minus 10, and then plus ut minus 1 convolve with ut minus 11. So if I convolve ut with ut, I will get ramp signal. So that this ramp signal, how we are getting ramp signal, this I have already talked about in week 6 live session. So you can refer to week 6 live session for this particular representation, how this basically comes. So ut convolve with ut will give you rt, or the ramp signal, and this will give you a delayed version of ramp, as because I'm convolving a ut with a delayed version of ut. So I will get ramp at 10, then I will get ramp at 11 minus, so here also ramp at t minus 11, and then here I will get ramp t minus 12. So I can write it as r t minus 10 minus 2 into r t minus 11 plus r t minus 12. So this is what y80 looks like. So y80 is rt minus 9. Okay. So this is rt minus 10. So rt minus 10, 2 into rt minus 11, and followed by that we have r of t minus 12 plus r of t minus 12. Now I can just try to visualize how this y80 looks like. So the y80 starts at a position of 10. So at index 10, then index 11, and then index 12. So we need to just see that how the that over here actually how the slopes have been changing. So we need to calculate the slopes. So for this particular operation, we have to see that given this particular, I guess there have been some issues happening with the pen. Okay. So while advancing this particular signal, so what we had done is that, so zeroth sample will initially the sample was like this 0 to 1. And when we are going to the negative side, so while advancing the signal with an amount of 10, so zeroth sample will go to minus 10. and the first sample it will go to -9. So for example, 0 minus 10 is equals to -10, and 1 minus 10 is equals to -9. So these are the time ranges. So the signal will go to -10 to 9. So let me just write it -10 to 9, and over here I will get 9 to 10. So here also it will be 9 to 10, as because I am just doing the time reversal. So let me just redo the calculations over here. So it will be 9 and it will be 10. And then over here, so it will be, let me just redo the calculation, ut convol with ut minus 9, then ut and then finally it will be ut minus 1 convol with ut minus 10. So I can write it as ut minus 9, then it will be ut minus 10, then it will be r of 10, it will be r of t minus 9, r of t minus 10. Again, this will give you r of t minus 10, and at this particular position, it will give you r of t minus 11. So therefore, if I just combine all these results over here, so I will get t minus 9, t minus 10, and t minus 11. So if I just make changes over here, it will be t minus 9, t minus 10, t minus 11. So what we did initially is that while advancing the signal, I just have wrote -10 and -11. So I have mistakenly wrote that -11 part. So it will be somewhat -10 and -9. So if I use the -10 -9 operation, so then I will get the particular signal over here. So y80 is equals to rt minus 9, 2 into rt minus 10, and rt minus 11. So now we need to see that how the signal looks like by 80, how it looks like. So we need to calculate the slopes. So the signal is initially starting at a position of 9, and the initial slope is 1. So this is the initial slope. So here slope is equals to 1. Now when I reach to 10, t equals to 10, the amplitude is 2. Okay. However, I can see that the slope is basically 1 minus 2. So 1 minus 2 will give you the slope of -1. That means from here it will start falling down. So here the slope is equals to -1. Now what will happen after 11? The 11th index. So after 11, the slope is equals to -1 plus 1, 0. That means now there will be no slope. That means only a straight line around this x-axis. So therefore, this is slope is equals to 0, and over here also slope is equals to 0. So therefore, this is the signal, and the signal will have a range of 9 to 11. So let's just check. So over here, the signal has a triangular pulse. So this is what It is a triangular signal, and the time range is in between 9 to 11. Okay, so let's move to the last question for week 6 quiz. So the representation is given as xn is equals to 2 sine pi by 4 n plus pi by 3 and then cos 3 pi by 4 n. And we have been given a filter whose DTFT is given over here. So the DTFT is a e to the power minus j to omega, and it is bound between omega equals to plus minus pi by 2 and it is minus pi by 2 or pi by 2 omega pi. So if I draw the magnitude plot of this particular filter, so h e power j omega, and I am just plotting the magnitude plot part only. So I will take a magnitude of mod of e to the power minus j2 omega. So e to the power minus j2 omega, if I take magnitude, so I will get 1 only. And as because a is multiplied over here, so I will get a. For the whole region of minus pi by 2 to pi by 2, I will get magnitude of a. Or let me just write it clearly. So the magnitude is a. And thereafter, till pi and till minus pi, the value is 0. And over here, the value is a. Now, this is the filter that have been given, and we need to find what is the output of the filter. That means, given this filter f, we are providing an input of xn, and this is output yn, and we need to find what is yn. So let's check with filter characteristics. So filter characteristics will give you some hint. So this filter has a passband between minus pi by 2 to plus pi by 2. And the signal, input signal, has a frequency response at 3 pi by 4. So 3 pi by 4 is it basically exceeds this passband region. So therefore, this 3 pi by 4 will be deleted. So this will be deleted. So now I need to just worry about what will happen with this particular sine pi by 4 n. So this is a phase added with this. So we'll not bother about phase as far as the passband is concerned. In this passband, what we have is that there have been this particular frequency is lying. So pi by 4 is inside this particular passband. So that means this sine pi by 4 n, this particular uh, signal component will be passing through this filter response. So we need to see that h e power j omega is having a to j omega, and let me just write it in the z domain. So a z to the power minus 2. So if I try to find what is hn, then I will just take convolution between hn and this particular component so that I can get the final output. So if I take inverse z transform, I will get hn and I have to take inverse Z transform in this particular region also. So let's start finding the inverse Z transform of H of C. So this is A Z to the power minus 2. So if in the time domain the signal is 1, or let's say if in the time domain the signal is delta n, see the Z transform will be 1, and if I multiply Z to the power minus 2 with 1, I will get delta n minus 2. So therefore, Hn I can write it as A into delta n minus 2. Fine. Now we need to convolve this Hn component with 2 sine pi by 4 n plus pi by 3 component. So Hn is A delta n minus 2 convolve to sine pi upon 4n plus pi by 3. So we know that if xn is convolved with delta n minus k, so the output will be x of n minus k. So by that relation, I will get 2a sine pi by 4, and in place of n, I will get n minus 2 plus pi upon 3. So this is what yn looks like. So let's just copy this part and paste it over the first page, and let's just check, compare with the given solutions. So this is what we have achieved, and it is matching with option D. Therefore, option D is the correct answer for this question. So with this, we have covered the week 6 quiz part, and now we'll be heading to the recap part of week 7 content. So in week 7, we'll be seeing that how to design an IIR filter, and already I have told that while designing an IIR filter, digital IIR filter, we cannot design the IIR filter directly. So for that, what we have to do is that we have to revisit some concepts of analog filter design. We have to design an equivalent analog filter over there. And then from the analog domain, we have to remap that analog filter response to the digital domain filter response. So we'll get some Fourier transform representation in the analog domain, and from that Fourier transform representation, we'll get the uh, magnitude spectrum. That magnitude spectrum, what we can do is that we can remap that magnitude spectrum into the digital domain, and we can get the DTFT. Subsequently, from the DTFT, we can construct the Z transform representation. And then if I just take the uh, inverse Z transform, I will get H of n. So by this process, let us start revisiting the IIR filter design that has been covered in week 7. So before that, let me just give you some brief idea about some of the analog operators that we'll be using for this particular week. So let us consider there is a square pulse is given, which is lying in between minus t to t, and the amplitude is 2t. Now I'm asking you to shrink the width of this particular analog pulse. So I have squeezed this particular analog pulse over here. And then if I just make the t tending to 0, so when t basically tends to 0, and I mean the amplitude, let us consider the amplitude is 1 by 2t. So the area under the curve is equals to 2t multiplied with 1 upon 2t. So area under the curve is 1. That means if I integrate this particular impulse, this particular pulse, so I will get the area under the curve, or the integral value will converge to 1. Now, now I need to squeeze this particular band, so the baseband will be squeezed. Therefore, the t will tend to 0. If the t is tending to 0, so the amplitude is 1 upon 2t. So as t tends to 0, this will tend to infinity. So that means this will become very narrow, and this height will shoot up to infinity. So 1 upon 2t tends to infinity, and this plus minus t, or t tends to 0. So this basically arises the condition of a Dirac delta function, what we call as delta n. So at n equals to 0, if I squeeze this particular square pulse too much, such that the time is tending to 0, therefore the amplitude corresponding to that particular pulse is reaching to infinite. So that basically arises the condition which is called a delta t signal, or as because we are working with analog, I just have uh, I have to deal with the continuous time index. So this is the index. This is the axis is with respect to time t, and the signal is delta t, or what we call it as Dirac delta function. And if I multiply, so another relation corresponding to this particular delta that I have already told, that delta t, if I take integration del t dt, so as because this area, still the area will be 1 only. So if I take limit t tends to 0, 2t into 1 upon 2t, still this limiting value of this integral will still be 1. So therefore this integral will still be 1, and the delta t will exist at t equals to 0 and 0 otherwise. And we have to see the convolution relation. So convolution relation is, let's say, x a t convolve with del t. So it is just same as what we have seen in case of digital. So in case of digital, we had used summation. Now, as because we are dealing with the continuous time variable, so instead of summation, we'll be using the integral part. So integral minus infinite to infinite, it will be xa tau delta t minus tau dt. So this is what is the convolution, and we already have seen that if I convolve xa t, any signal with del t, I will get xa t back. So xa t convolve with del t will give me this thing. Similarly, if I do xa t convolve with delta t minus tau, I will get xa t minus tau, or I can readily say that evaluated at tau. So in this particular fashion, we'll just start the Laplace transform. So this is some basic recap of any what is basically called the Dirac delta, then the convolution part, and what is the output of a convolution with delta t. Any signal is convolved with delta t, I will get the same signal. Then we'll talk about the Fourier transform. So here also, if I take a system a to the power t, this is the system which has impulse response HAT, and the input is AT, then YT I can write it as minus infinite to infinite HA tau x of t minus tau t tau. So this will give you minus infinite to infinite. So it will be HA tau then it will be A t minus tau d tau. Then HA tau multiplied with a to the power minus tau d tau, and a to the power minus t I can take it out from this integration. So it will be a to the power t. So therefore we can see we had given a to the power t as input and output is some delta a or some lambda a multiplied with a to the power t. So that means I can refer it as eigenvalue and at is called as eigensignal. Now this basically gives you the flavor of Fourier transform. So Fourier transform H j sigma is equals to minus infinite to infinite H a t e to the power minus j omega t dt. So this will, so instead of small omega, let me write capital omegas because we are working with the analog frequency. So I will denote analog frequency by this and digital frequency by this. So h j omega is equals to minus infinite to infinite, and followed by that it is h a t to the power minus j sigma t dt. So this happens when a is equals to e to the power j capital omega. So this is the Fourier transform. Now, likewise, I can take the inverse Fourier transform in this fashion. HAT will be 1 upon pi, 1 upon 2 pi, and the range of the integral will be minus pi to pi. And then I can write it as H j omega e to the power j sigma t. And as because I need to get the time function back, I have to take the integral with respect to omega itself. So there will be a d omega over here. Okay. So after that, the stability is also another crucial point. So if HAT is a system impulse response, and if I have to ensure the stability, so stability will be defined like this. HAT dt should be yield, this integral should be yielding some finite value which is less than infinity. That means the impulse response should be absolutely integrable, and which we had already seen in case of digital signals. In case of digital signals, the stability condition was the absolutely summable. So absolutely summable. In case of digital domain, the relation was the signal should be absolutely summable, or if I just have to write mathematically, it would be h of n mod should be His summation should yield to a finite value which is less than infinity, and if this basically satisfies, then we can say okay, the signal of the system is basically stable. Now we have seen that the Fourier transform is basically is of this form: minus infinite to infinite h a t e to the power minus j sigma t dt. So that means we are considering the basis in the form of e to the power minus j sigma. That means we are only bothered about the imaginary part. So the basis function basically includes the imaginary part. So instead of considering an imaginary part, if I consider a more generic number representation, which is I will denote it with S, and which comprises sigma plus j omega, j capital omega. So sigma plus j omega is containing the real part as well as the imaginary part. So if I consider S is equal to sigma plus j omega, so this integral will be of this kind: h of s is equals to minus infinite to infinite h a t e to the power minus s t dt. Therefore, the relation is reduced to what we call as Laplace transform or S transform. So that means for this particular operation, we will be bothered about both the sigma and j omega part. However, in this case, only we were bothered about the j omega based basis functions. Now over here, we are considering both the real part and imaginary part in the basis. Now we need to see the stability corresponding to this HS. So if I take mod of this particular integral, so minus infinite to infinite HAT e to the power minus ST dt. So I can write it as minus infinite to infinite HAT e to the power minus sigma t into e to the power minus j omega t dt, and then the mod is closed. Now from the complex formulas, we know that mod z1 plus z2 is less than of mod z1 plus mod z2. So by that logic, I can write it as less than minus infinite to infinite. I can take the mod inside now, and I can write it as HAT, then e to the power minus sigma t, and e to the power minus j omega t dt. And I can write mod z1 multiplied with a mod of z1 multiplied with z2 is nothing but mod z1 multiplied with mod z2. So using that particular relation, I can write it as HAT mod e to the power minus sigma t, and mod of this thing will effectively give you 1. E to the power minus j sigma t will give you 1. So therefore, I can write it as like this. So to converge this particular integral, now we can see there is no contribution of this imaginary part. Only the thing that matter is basically the real part. So if this real part is such, your integral is converging. So that means for those particular sigma, the Laplace transform will be valid. Otherwise, if the sigma is such that your integral is not converging, that means for those particular sigma, the Laplace transform will not be valid. Therefore, the S transform basically instantiates the property associated with that, which is called the region of convergence. That means for some particular sigma, your S transform will be valid, or for some particular sigma, your S transform will not be valid. So we need to find what is the region of convergence, like what we have found in case of Z transform. So in Z transform, we have to explicitly mention that what is the region of convergence, as because region of convergence basically gives you the unique representation of any Z transform. And similarly, in case of S transform also, you need to find the ROC, as because ROC gives the unique representation of S transform output. So for that, if I start calculating that how the region of convergence will look like. So for example, here we have sigma, and let's take, we have 2 points, S1 and S2. So S1 is sigma plus j omega. Sorry, again, I'm doing the same mistake. So sigma plus j omega 1 and sigma plus j omega 2. And omega 2 is greater than omega 1. So visually it can be seen omega 2 is greater than omega 1. So for this S1 and S2, let us check that which of the for which of the cases the integral is basically valid. So I can see that HAT is there and e to the power minus sigma t is there. So which is same for this S1 and S2. However, this omega 1 and omega 2, this will not contribute in the validity of this particular integral. So therefore, at this particular line, for all the points, the sigma are same. For all the points, the sigma are same. So that means this, in case of S transform, the ROC lies, the ROC in S transform lies in the vertical strips. Vertical strips. Whereas in case of Z transform, we had seen that Z transform is basically something like this. Either it could be a annular ring also. So here, instead of that, these ROC basically lies in the what we call the vertical strips. And if I consider sigma is equals to 0, then it will give me a special case. So if I just plug in sigma is equals to 0, it will be minus infinite to infinite HAT dt. So this is nothing but the stability condition of signal. That means whenever the Laplace transform or the ROC of the Laplace transform encloses the j omega axis, that means here sigma is equals to 0. That means this is the j omega axis. So when the Laplace transform encloses the j omega axis, then only will will comment about the system. Okay, the system or the signal is basically stable. So which was there in case of Z transform? If the Z transform basically encloses the unit circle, we could have said that the system or the signal corresponding to which we are calculating the Z transform, that is stable. So if I take analogy over here, so that unit circle basically reduced to the j omega axis in case of Laplace transform. Now with this, we have built sufficient amount of theoretical sense to start with the digital IIR filter design. So already we have seen that, already I have told that while creating the digital IIR filter, we cannot draw the IIR filter characteristics directly. So for that, we need to first draw or first construct a equivalent analog filter, and then the analog filter from that analog filter response, we have to remap that response to the digital domain, and then we can get the DTFT relation. From the DTFT, I can get h of n, and from h of n, if I take again the z transform, I will get the transfer function representation of the analog filter. So let us consider. And here, additionally, what I had just missed is that the ROC will lie over here, and for a causal and stable system, already we know that pole should lie in the left half plane of the S plane. So if this is the S plane, where this is sigma and this is j omega, pole should lie in the left hand side. So this will ensure the stability, and the ROC will not contain any poles. So ROC will not contain any pole. And if the system is causal, so as we have already seen in case of Z transform, also in case of causal signals, the ROC is basically divergent, or it goes outwards direction. So here also, if this is the farthest pole, so say poles are residing over here also, and this is the farthest pole. So ROC will start from here. So it is enclosing j omega axis. That means it is stable, and from here, from the pole position itself, we can see that none of the pole is going in the right half plane. So therefore, the poles are lying residing in the left half plane. So which basically ensures the stability of the system. And additionally, we can see that j omega axis is enclosed using the ROC. So therefore, it also signifies the stability of the system. Additionally, as the ROC direction is divergent, so therefore we can say that the system is causal system. So a causal system will have a divergent ROC, and it should enclose the j omega axis. The ROC will enclose the j omega axis, and the position of each of the poles should be in the left up plane of the left hand side of the S plane. So let's start constructing a analog filter. So let's start designing a filter which has this particular response. So H j omega magnitude square, and this is your sigma, and this is bounded between minus sigma c to sigma c. But there is a problem with this particular response. The problem is there is sharp transition at this particular region, which, and over here too. So this sharp transitions basically raises the condition of discontinuity. And as far as analog signal processing is being concerned, so this particular discontinuity we cannot basically deal with analog signal representation. So instead of getting the exact brick wall characteristics of a filter, so this is we call a brick wall characteristics. So there is a pretty sharp transition over here. It is like just a brick wall. So this brick wall characteristics, instead of using this brick wall characteristics, we use some approximating function which tries to resemble the same characteristics like this filter. So this approximation functions could be, one such of this approximation function is Butterworth function. So the Butterworth function the magnitude response of the Butterworth function can be written as magnitude of h omega square will be 1 plus omega c to the power 2. But mind it, this is a magnitude square response. So we have not even talked about what is the Laplace transform of this particular representation and all. So that we have to find. So what is the Laplace transform and other representations? So as far as filters is being concerned, so any filter, Laplace transform of any filter should be in the order of should we have this particular representation ns and ds. So this will give you the transfer function representation. So let us consider we have b naught, b1s, b2 s squared, and then bq s to the power q. And over here we have a naught, a1 is a2 s squared plus ap s to the power p. Now if I take if s is equals to j omega, it will be simply h of j omega is equals to p naught b1 j omega. Sorry, again I'm doing the same mistake. So b1 j omega, b2 j omega whole square. So better to write in parentheses. So pq j omega q divided by a naught a1 j omega a2 j omega square and then ap j omega p. But now if I take ha j omega square, so this will give me what we call magnitude spectrum. That means with respect to the frequency values, how the magnitude is changing, I can get the relation from this particular h j omega magnitude square. And already we have shown that the approximation function for this Butterworth filter that we designed is of this kind. So I can just paste this thing over here. So here again, same mistake is there. So sigma c. So if I try to take an analogy between this brick wall characteristics, so this is the standard brick wall characteristics that I am very happy to achieve. But as because due to continuity constraint, so I cannot get this kind of brick wall characteristics. Instead of that, I will try to maintain some similar properties in the passband, and here I will see that there will be some attenuation effects. So when sigma is greater than sigma c, so this is what sigma c and this is also sigma c. So when sigma is greater than sigma c, that means this one is high and this one is low. Therefore, this will give you a high value, and therefore 1 divided by very high value will give you low. Then one point will come when sigma is equals to sigma c. So let us consider initially this has one amplitude of 1. So when sigma is equals to sigma c, it will be what? It will be 1 divided by 1 plus 1. That means half. So at this particular location, the amplitude is half. And over here, when sigma is less than sigma c, let us consider at this particular when the sigma value is very, very less than sigma c, then what will happen is that 1 divided by 1 plus. So sigma c is now high. So therefore, this value will be close to 0. So the output will be 1. So that means now I can draw an analogy like this. So this will be and over here it will be it will try to give you for some portion of time, it will try to give you a pass band with amplitude 1, and then you will see that there is some attenuation effect is being observed over here. So here I can see that the attenuation effect starts. But this is quite common as because we are trying to approximate this breakable characteristics using this Butterworth function. So this is a very coarse function. So this function tries to uh, approximate the breakable characteristics by providing this sort of frequency characteristics. So this I can write it as, so mod z squared, I can write it as z multiplied with z star. So therefore h j omega multiplied with h j omega star, and h j omega if it is b naught plus b1 j omega b2 j omega square, and then bq j omega to the power q divided by a naught a1 j omega dot ap j omega to the power p. I have just substituted s by j omega. So now if I take the star, so if I take star, I will just write some properties. So z1 by z2 star will give you z1 star, z2 star. Okay, so this I can just, I will just try to make the process faster now. So instead of taking whole star, now I will take two stars at both the locations and z1 plus z2 start. So I can see all the summation components are there, and so I'm trying to make some analogy over here. So z1 plus z2 star will give you z1 star plus z2 star. So over here I can get b naught b1 minus j omega b2 minus j omega square, and likewise. So it will be, instead of that, let me start writing in terms of star itself. So star and then j omega plus j omega squared, and then I can take star over here, and then bq j omega to the power q, and then I can take star. And likewise in the denominator also I can do the same operation, j omega star plus dot a to the power p j omega to the power p, and then I can take star. And if second property, so that is why I have I just have skipped the last step. So I can write z to the power p, and then if I take star, it will be same as z star to the power p. So I can just take the star operation inside. So it will be b naught b1 minus j omega, then b2 minus j omega, and then I can take square. Likewise bq minus j omega, and then I can take this thing, and likewise over here also I can take. So in the denominator also I can do the same operation. So it will be same as uh, ha star j omega. So this is nothing but instead of just putting j omega, now I am putting minus j omega. Otherwise, rest of the operations are same. So finding uh, finding h star j omega will nothing but h of minus j omega. Therefore, I can write ha j omega squared is ha j omega multiplied with ha star j omega and I can write it as HA j omega multiplied with HA minus j omega. And now I can convert it in the S domain also. So HA is squared is HAS and HA minus S. Okay. And it was given that this particular representation is basically equated with 1 divided by 1 plus sigma divided by sigma c, then whole square. So I can multiply z in both numerator and denominator. So, and I know that S is equals to j omega. Then I can convert this particular operation as S by j omega c whole square. So HAS whole square is equals to HAS HA minus S 1 divided by S plus j omega c to the power, sorry, there was 2n. So this is 2. And now we have got some representation which resembles like a transfer function. So using this transfer function representation, we now need to check the poles of the system, as because if the poles are been in the location like they are in negative half side, so we can comment about the stability of the system. But mind it, we are trying to find the poles. So I will use this particular factor to find the pole of this system. HAS mod square. I am not finding the pole of HAS or HA minus S. So I cannot comment about what HA is, whether this is stable or not, but I will be comment about HAS square. So to find poles, I will make 1 plus S j sigma c to the power 2n is equals to 0, and then S by j sigma c will be minus 1 and there will minus 2n, and then I can write it as j sigma c, and this I can write it as e to the power j 2k plus 1 divided by 2n multiplied with pi, and e to the power j, this thing I can, so j could be written as e to the power j pi upon 2. That means cos pi by 2 will be 0 and sin pi by 2 is 1. So 0 plus j, it is j. So e to the power j 2k plus 1 divided by 2n multiplied with pi, and there is a phasor with e to the power j pi by 2. So that means there will be a phase shift of plus pi by 2. So in the S plane, if I start constructing the poles location, so this will be a circle which has a, so this is basically in the form of r e power j theta. So this r is the radius and this radius is sigma c. And now I have to check that what is the location of the pole. And the k will contain the value 0, plus minus 1, plus minus 2, plus minus 3, and there are total n number of 2n number of roots of this particular equation I will get. So that means 2n number of poles I will get. So I can write it as 2n minus 1. So 0 to 2n minus 1. So that means total 2n number of values will be there. And the roots of the equation has already been given that it is 2n. So this is satisfied that I will get 2n number of roots from this particular equation, which are basically poles of the system. And if the when I consider that k is equals to 0, so when k is equals to 0, it is e to the power j pi by 2n. Let us consider at this particular position. However, I am getting some phase shift of e to the power j pi by 2. So I will be shifted by pi by 2. So so this particular position will map over here. So likewise, every pole will be shifted by 90°, and these are the pole locations about the circumference of this particular circle. So now, as already I have told that this is the poles of HAS mod square. So HAS mod square is HAS multiplied with HA minus S. So here I can see that some of the poles are lying at in the left half plane LHP. So I can allocate these poles to HAS. So if I allocate these poles to HAS, so I can see that okay, all the poles are residing in the left half plane. So it basically gives you the possibility of a stable system. And as because the poles are lying in the left half plane, so the ROC will consider the farthest pole location, and from the pole location I can get the ROC like this. So this will give you a causal system, as because in case of any filter we try to find a causal and stable representation. So HAS, now with this particular provision, if I consider the left half plane poles which corresponds to HAS, then I can say this system is stable in, and HA minus S will consider the poles which are lying in the right hand side part. And if I multiply these two, I will get the whole system. So therefore, effectively, my system has been now stable. So given this particular HAS, now this is an analog filter we have the analog filter we have already given, and I can see the magnitude spectrum. Now in the lecture 2, we have seen that what is the relation between our digital frequency and analog frequency, and what is the relation between digital Fourier transform and analog Fourier transform. So this is basically the analog Fourier transform, analog Fourier. So I can convert this analog Fourier to digital Fourier, and from there I can get Hn, and from there I can get the H of Z. So in this way I can construct any form of AR filter by starting the construction of the analog equivalent filter, and then from the analog equivalent filter I will get the analog Fourier transform. I will remap it to digital Fourier transform. Then I can get back the H of n by taking inverse DTFT. And if I take inverse DTFT and then I take Z transform, I will get the transfer function representation of the digital filter. So with this, let's start solving this problem. So these are the problems which are for week 7 content. So in case of week 7, so the question is that, so this is a practice question. So this practice question deals with a low pass filter is described with this particular equation. The filter is converted to a high pass filter by giving a pi right shift to h e power j omega. So let us first find what is h e power j omega. So let's take Z transform on both sides. So I will get yz equals to 0.9 Z to the power minus 1 yz minus 0.18 Z to the power minus 2 yz, 0.5 xz, 0.1 Z to the power minus 1 xz. So yz upon xz will be 0.5. Obviously, there is a minus, and then 0.1 z to the power minus 1, and here it will be 1 minus 0.9 z to the power minus 1 and 0.18 z to the power minus 2. So this will give me hz. So if I write z is equals to r e power j omega, and we have seen that when r equals to 1, so z is equals to only e power j omega. So this becomes, so at that time, the z transform becomes the DTFT or discrete time Fourier transform. So I can replace z with e to the power j omega. So I can write h e power j omega is equals to minus 0.5 plus 0.1 e to the power minus j omega divided by 1 minus 0.9 e to the power minus j omega plus 0.18 e to the power minus 2 j omega. And now we have been given in the question that we'll be providing a pi right shift. So pi right shift means if we have been given h e power j omega, then pi right shift will give me h e power j omega minus pi. As because we are shifting the signal in the right direction, that means there will be a delay component associated with the for it DTFT. So instead of h e power j omega, I will get h e power j omega minus pi. Now, while replacing omega with omega minus pi with equation number 1, I will get h e power j omega minus pi is equals to minus 0.5, 0.1 e power minus j omega minus pi, 1 minus 0.9 e to the power minus j omega minus pi, 0.18 e to the power minus j omega minus pi, and a factor of 2 is multiplied over here. Now e to the power minus I theta is equals to cos theta minus j sin theta. Now we have to see what e to the power minus j omega minus pi will look like. So it will be cos omega minus pi minus j sin omega minus pi. So cos theta is equals to cos of minus theta. So it will be cos of pi minus omega. However, sin theta, sin minus sin theta is sin of minus theta. So therefore it will be plus j sin pi minus omega. Now let's just revisit the basic trigonometric relations. So all sine, tan, cos. So cos pi minus omega will be cos omega, but as because this is not the domain of cos, so it will be minus cos omega. However, this over here, it will be j sine omega itself, as because this part is restricted for sine. So if I take negative common, so it will be cos omega minus j sin omega. It will be minus e to the power minus j omega. So therefore, e to the power minus j omega minus pi will be minus e to the power minus j omega. Similarly, if I have to find e to the power minus 2j theta, so for that it would be cos 2 theta minus j sin 2 theta. Now in place of theta, now let me replace omega minus pi. So it would be e to the power minus j 2 omega minus 2 pi. So cos of 2 omega minus 2 pi minus j sin 2 omega minus 2 pi. Again, all sine tan, and cos. So it is cos 2 pi minus 2 omega minus j sine. So if I just take the opposite part first, so 2 pi minus 2 omega, so it will give you plus over here. Now 2 pi minus 2 omega, so it would be cos 2 omega, and 2 pi minus 2 omega that means it is lying in this particular coordinate, so fourth coordinate. So fourth coordinate is reserved for cos, so it will be cos 2 omega, and over here it is reserved as it is reserved for cos, so for sine it will be minus, so j sine minus 2 omega. So it is same as e to the power minus j 2 omega. Therefore, e to the power minus 2j omega minus pi is equals to e to the power minus j 2 omega. So these two relations we have just found, and which will be exploiting to find the relation over here. So this was what omega minus pi. So minus j omega minus pi. So this will be 0.5 minus 0.1 e to the power minus j omega divided by 1. It will be plus 0.9 e to the power minus j omega, and it will be plus 0.18 e to the power minus 2 j omega. And I can write it as h2 e power j omega. This thing I can just considering I'm getting some different h. So this h2 e power j omega. So I can write h2 e power j omega as x e power j omega divided by y e power j omega divided by x e power j omega. And then if I cross multiply these two, then if I cross multiply these things with each other, then I will get the filter representation or the input output representation. So now I am writing in terms of z. So yz plus yz 0.9 z to the power minus 1, then 0.18 e to the z to the power minus 2 yz followed by 0.5 xc, and over here it was minus j omega. So z to the power minus 1, 0.1, and then x of c. So if I just take inverse z transform, so I will get yn is equals to minus 0.9 yn minus 1 minus 0.18 yn minus 2. And then, okay, sorry, there was minus over here. So minus 0.5 x of n, then minus 0.1 x of n minus 1. So this is the final answer for this particular question, and let us just check which one of this actually resembling the same form. So it would be minus 0.9. So these two options are nullified, and this is minus 0.18. So this option is also nullified. So option C is the final answer. Now the last question for this week is HAS is 2 divided by S cube plus 9s square 23s plus 15. So we have to use an impulse invariance method, and we need to find the HAT is the impulse response of analog filter. HAT is sampled with a period t, and if it is sampled with a period t, then I will get a what you call the sampled signal or discrete signal. And for that discrete signal, if I take the Z transform, So then where the poles will lie. So for this, what I will do is that first I have to find the uh, analog filter response. So analog filter response, how I will get is that I have been given a Laplace transform. So I need to take the inverse Laplace transform. So let's start factorizing this part first. So s plus 1. So there is a factorization technique is there. So s plus 1 and then again s plus 1 and s plus 1. So I can write it as s square. So it will give you s cube plus s square plus 8s. That means 8s square, then 8s, then 15 will give me 15s plus 15. So if we just sum this all up, so we will get the same representation. So this is 2 divided by s plus 1, s square, 8s plus 15, and 3 cross 5 is 15. So this will effectively s plus 1, s plus 3, s plus 5. So I can write it as a by s plus 1, b by s plus 3, and c by s plus 5. So HAT I will get from the inverse Laplace transform of HAS. So in the next page, if I proceed, HAT is inverse Laplace transform of HAS. So I can write it as inverse Laplace of a by s plus 1, b by s plus 3, c by s plus 5. So Laplace inverse of a by s plus 1, Laplace inverse of b by s plus 3, and Laplace inverse of c by s plus 5. So if I do this, I will get a e to the power minus t, b e to the power minus 3t, and c e to the power minus 5t multiplied with ut. So this is what my HAT looks like. Now I can get Hn by taking the samples with a period of t. So which is given as HA_NT. So I can write Hn is equals to, in place of t, I will be using NT. So a e to the power. So this is HANT is e to the power minus NT, b e to the power minus 3NT, c e to the power minus 5NT, and then u of NT. Now I can write it as h of n, and I will take some modified version. So a e to the power minus t, then n, then b e to the power minus 3t, then n, and c e to the power minus 5t, then n. And I can write it as, if Hn I am getting from HANT, so from UNT I will get UN. So Hn is represented using this particular representation. Now what I have to take is that I have to take a Z transform. So Z transform, that means Z transform of A e to the power minus t n, b e to the power minus 3t n, c e to the power minus 5t n, un, and there will be another bracket. So I have to take Z transform of this representation. So if I take Z transform of this representation, I will get HC in the form of numerator and denominator. And if I take dz is equals to 0, I will get the cis poles of this particular system. And from there, I can comment about what is the stability, what is whether the poles are lying inside the unit circle or not, and associated to that I can comment about the stability of the system. So here they have not asked those questions, they just are worried about the locations of the poles. So I will just show you that how we can take the Z transform and we can find out the poles of the system. So HZ is Z transform of A e power minus T to the power n un, Z transform of B e to the power minus 3T n un, Z transform C e to the power minus 5T n un. Now, we know the relation a to the power n un. It has a Z transform of 1 minus a Z inverse. So therefore, if I take the Z transform of this particular representation, I will get 1 minus e to the power minus T Z to the power minus 1, followed by B 1 minus e to the power minus 3T Z to the power minus 1. C 1 minus e to the power minus 5T Z to the power minus 1. So this is what HZ looks like. And if I now combine these three forms, so I will get e to the power minus T Z to the power minus 1, 1 minus e to the power minus 3T Z to the power minus 1, 1 minus e to the power minus 5T Z to the power minus 1. And I will get some numerator of Z, because I'm not bothered about the numerator part, because numerator part will not give me the location of the poles, because this basically corresponds to the zero locations. So I'm not solving for the numerator part. So I'm considering, as because this is a function of C, I can just write n of C. So if I make this thing equals to 0. So individually 1 minus e to the power minus T Z to the power minus 1 equals to 0, 1 minus e to the power minus 3T Z to the power minus 1 equals to 0, and 1 minus e to the power minus 5T Z to the power minus 1 equals to 0. So this will give me 1 is equals to e to the power minus T by Z. So Z is equals to e to the power minus T. So therefore Z is equals to e to the power minus T, e to the power minus 3T, and e to the power minus 5T. So these are the all locations of the equivalent IIR filter. So let me check e to the power minus T, minus 3T, and minus 5T. So this one. So this is the correct answer for this particular question. So with this, we have covered numerous amount of questions which comprises the solution of week 6, and additionally the recap of week 7 content, and some questions which are related to the impulse invariance methods and filter designing techniques in the digital domain. So with this, I conclude this particular session, and if you have any queries, you can ask. Let me just save this one. So I will be uploading the video and the slides by tomorrow itself. So if you have any further queries, you can just post your questions in the NPTEL forum itself, and I will try to answer those questions over there itself. And additionally, from the next week onwards, I will follow the previous routine. That means I will conduct the session from on Friday itself. So I hope no further questions are there, so we can stop the meeting over here. And thanks for joining.